Section 4.4, Precipitation Reactions. Apply the solubility guidelines to predict the formation of a precipitate and reactions of ionic compounds in aqueous solutions. So, what do we have? Ionic compounds in an aqueous solution. Question is, does a precipitate or a solid form? Write and interpret ionic and net ionic equations for precipitation reactions. We're going to do all that. Okay, solubility of ionic compounds. Ionic compounds that readily dissolve in water are considered soluble. Ionic compounds that do not readily dissolve in water are insoluble. Easy peasy. You can look up the solubility of an ionic compound in table 4-5, which we're going 4.5, which we're going to see on the next slide. Okay, here it is. We've got a key here, and within this white area, we've got S indicating soluble, I indicating insoluble, SS indicating slightly soluble, and lowercase d indicating decomposes in water. Interesting, interesting. Okay, so this right here is a huge amount of information. This is an example of a solubility table. Now, the way that you can read this is any ionic compound that is found in this matrix, you'll be able to know whether it is soluble or insoluble based on that code that we just went over. And solubility does have a quantitative measure to it, and that is 1 gram of solute in 100 grams of water. Okay, so if you have more than 1 gram, so S, soluble, greater than 1 gram of solute will dissolve in 100 grams of water. Insoluble is indicated by less than 0.1 grams of solute in 100 grams of water. Slightly soluble is between 0.1 and 1 grams of that solute will dissolve in 100 grams of water. So think about this as if you put in less than 1 gram of basically anything in here, it's probably going to go into solution. But when you add more of it, does it partially go into solution? Does it completely go into solution? That's kind of where this insoluble, slightly soluble versus soluble comes into play. So with the amounts that we're using or discussing in this class, I want you to look at this as kind of hard lines. You're not going to have a question where it's like, oh, well, actually, I was saying this amount was added. If you see S, you can go ahead and operate. It goes into solution. When you get to Gen Chem 2, if you elect to take Gen Chem 2, you will talk about solubility products. So then you'll talk about amounts and you'll talk about whether or not something precipitates. Now, how do you read this, though? That's the skill that I want you to take away from this. If you saw something like, let's go with LiOH, lithium hydroxide, that's something that we can classify. We can classify that as a base. We can classify that, well, we can classify that as a strong base. And so the question is it soluble or insoluble? Well, you could roll the dice and say, I bet that it's going to be soluble because it's a strong base. But this table right here, well, Li is found right here. Then what we want to do is look at each one of these columns and find the column that has hydroxide. And that column that has hydroxide is at the very end. And so in the first row versus OH, that's going to be soluble. Okay. Now, if you had something like CaOH2 on the other hand, well, you got to find calcium, the calcium ion, and then line that up with your hydroxide ion, which is again down here. That would be slightly soluble. Okay, so working with this is find your cation on the left-hand side, and then read that matrix through till you find your anion. So whatever compound you're looking for, that's the way that you're going to do it. Now, for your exams, you'll be given some variation of this, possibly condensed. I do not want you to commit these to memory. What I would recommend, however, is look at some of the general trends. For instance, this first row, nitrates, perchlorates, hypochlorites, and Acetates, what do they have? They have S up and down the row. So any cation that you pair with any one of those, you're going to make something that is completely soluble. Meanwhile, if you go over here, carbonates, sulfites, phosphates, and chromates, almost all of those are going to be insoluble. Are there exceptions? You betcha. But I want you to look at these as kind of like, are there some emerging trends? And are there some emerging, trends, I think is just a good way to look at it. But like I said, this isn't going to be something that you have to commit to memory, but the more that you see these sorts of things, the more you'll save yourself some time. So if I gave you a solubility chart on an exam, and then I asked you about an acetate or something like that, you'd be like, I'm not even going to waste my time looking at the solubility chart because I know that acetates across the board are going to be soluble. Okay, now looking at this table right here. Are the following salts soluble or insoluble in water? Okay, so this is kind of a tricky question. Well, it's really not a tricky question, but it's a question nonetheless. And I'm just going to kind of ruin it for you. I've got this chart open in another window on my computer, so I'm toggling back and forth between that. But phosphates generally are going to be insoluble because, well, that was the row where we saw basically anything with a phosphate was going to be insoluble. But this asks specifically about sodium phosphate. Now, sodium happens to be in group 1. So this is an exception to the rule, and this is soluble. Okay, sulfates. Sulfates are, well, they've kind of got a mixed bag. I would say more than, almost half the time from what's shown on that table, they're going to be insoluble. But it depends on what you're pairing it up with. So magnesium sulfate happens to also be soluble. Ag2S, so we find Ag on the left-hand side of our screen. And then sulfide, so silver sulfide. Well, sulfides are generally going to, well, half the time they are insoluble. One instance they would decompose in water. This happens to be an example of an insoluble compound. So being able to read that table, read that matrix is very valuable and very helpful for you. That's what I said. Okay, now predicting the formation of precipitate. Precipitation reactions occur when solutions of two ionic compounds are mixed and undergo a double replacement to form an insoluble ionic compound. Now, when solutions of two ionic compounds are mixed, a cloudy substance may form, which is the precipitate, indicating that a reaction has occurred. Alternatively, when solutions of two ionic compounds are mixed, no change may be observed, indicating there was no reaction whatsoever. So maybe what you have is you have two homogeneous solutions, you mix them together, and after the fact you now have one homogeneous solution. No reaction took place there. So if you had, for instance, sodium chloride and silver nitrate, those are going to ionize in solution. And they're going to form hydrated ions, so that means those individual ions of Na plus floating around with a bunch of H2O molecules. This is my H2O. There we go. There's another H2O molecule. And there's our fourth H2O molecule. They're floating around in solution. They're going to dissociate. And what they're going to do is the cation from AgNO3, silver, is going to pair up with the anion from NaCl. So here is the result. We got AgNO3 plus NaCl results in AgAQ, NO3AQ, NaAQ plus Cl minus AQ. Now what's going to happen is this cation, which was previously in, I'm just going to say in cahoots with our NO3 anion, now is in contact with the chloride ion. The sodium comes in contact with the nitrate. Okay. Now, what's the fate of those? Well, I'll tell you this. Nitrates are almost always aqueous. They are almost always soluble. So if my head wasn't blocking the NaNO3 AQ, you would see AgCl, or sorry, you would see NaNO3AQ. AgCl, on the other hand, well, this happens to be a compound, silver chloride, that is solid, that precipitates out of solution.